Hello everyone, here we'll be discussing the dot product, which, like I mentioned in the previous video, is just something new we can do with vectors. It's a new operation. Basically, it's a way to try to describe some multiplication with vectors, with addition with vectors, and scalar multiplication with vectors and a number. There's actually some significance when it comes to like this geometrical perspective, you can say. So there's a visualization that goes along with it. With dot products, there's kind of a visualization, but it's way beyond what we want to discuss. So for right now, we'll just say this is the definition of what it is. And in the next section, we'll actually take a look at what is called the cross product, where instead of this dot multiplication, we'll use a cross times multiplication. And the definition is a little different. So for right now, let's just kind of take this definition as fact. So the dot product of two vectors u and v is u dot v, where u is u1, u2, u3, and v is v1, v2, v3. Now, this definition can go on to any dimension. In fact, we'll lower the dimension for this example with two-dimension vectors, but in this class we'll be very often using three-dimension vectors. So if you wanted to go beyond, then the definition would extend in a very similar way, and you can kind of see what that would be. But all we're doing is just looking at the components, multiplying those together, so u1 times v1 plus u2 times v2 plus u3 times v3. Now, one big thing to note here is that unlike with vector addition, this does not result in a new vector, but instead results in a scalar, because this is just literally a sum of numbers. So this is a scalar, not a vector. That's kind of interesting. Whereas, for example, vector addition, a vector plus a vector is a new vector, but here with the dot product, a vector dot product with another vector results in a scalar, not a vector itself. So that's something to note. So here let's take a look at this example with two dimensions. We want to multiply these two together, so it's 2 times 3, added to these two multiplied together, which is 4 times negative 1. So that, of course, results in 6 minus 4, which is 2. So the dot product of these two vectors is the number 2. Now again, what that means geometrically isn't obvious. In fact, we may discuss that later on, but I honestly don't think we need to. It's a little beyond the class, in my opinion. Now, the dot product of these two vectors in three dimensions will be negative 1 times 6, that, 7 times 2, so adding 7 times 2, plus 4 times negative 1/2. And of course, this is negative 6 plus 14 minus 2, which if you add the negatives first is negative 8 plus 14 is 14 minus 8, which is 6. So the dot product of these two vectors is the number 6. And now we have some properties that are pretty simple to justify on your own. I'm not going to justify them, but I'll talk you through them. So this says the dot product of a vector in itself is the square of the magnitude. This is actually very interesting and very useful property that will be seen a lot in this video. And I'll allow you to verify that on your own, but you can kind of see it here. I guess I'll help you verify it a little bit. Notice the magnitude of a vector is the square root of the sum of the squares of its components. So if you square it, you remove the square root part. So this says that the magnitude of a vector squared is just the sum of the square of its components. So if A, for instance, is A1, A2, A3, then this right-hand side is A1 squared plus A2 squared plus A3 squared. This dot product is A1, A2, A3 dotted with A1, A2, A3. So if you multiply component-wise and add those, you literally get A1 squared plus A2 squared plus A3 squared. So even though I didn't write anything down, it should be fairly easy to follow if you write it down on your own. Now, property 2 says that we have commutativity. Dotting two vectors in any order will result in the same thing. And that's just based on the definition that multiplication and addition are both commutative properties. 3 says that we have a distribution of dot product over vector addition, and allow you to kind of verify that on your own. If A is A1, A2, A3, and B is B1, B2, B3, and C is C1, C2, C3, you can write it out and use properties of addition, or I guess really definition of addition, vector addition, and scalar, not scalar multiplication, but dot products. Then you'll actually see this result definitely holds, or this property holds anyways. 4 says scalar multiplication with a vector A dotted with a vector B is the scalar C multiplied by the dot product of A and B. So this is interesting because CA is a vector, and dotting that with the vector B basically gives this associativity property of scalar multiplication and dot product. So that's nice we have that. And then lastly, the 0 vector dotted with any vector A is the number 0 itself. And that certainly makes sense because here basically what we're doing is multiplying every component of A by every component of 0 vector, which is 0. Adding those gives you 0. So that's pretty easy to justify and verify, I think. So now we're going to be taking a look at something a little different. Instead of doing an example using these properties, which we certainly could do, I want to instead take a look at the next idea, which involves looking at angles between vectors, where we'll be kind of seeing a visualization a little bit. Now, in this section, we won't really look at too much of a visualization of vectors beyond what we're about to see. So let's take a look at that right now. All right, so this next theorem here says that if theta is the angle between two vectors u and v, then this following equation holds. U dot v is equal to the product of the magnitudes of u and v multiplied by cosine of the angle that is in between them. Now we'll be discussing the proof of this because I think it's pretty relevant. In the sense that we'll see a lot of the properties we just saw in play in the proof, which is kind of nice. So instead of doing an example of each of the properties, I figured we just prove this, and then we'll be using this a lot throughout the video after this proof. So let's take a look at that. Now, like I mentioned previously, that is, we need a little bit of a visualization. I've drawn one here. So imagine we have this three-dimensional scenario where we have these vectors u and v, and the angle between them is our theta, let's say. And what we need now is we actually need the side opposite of theta that connects u and v. So I'll treat that side length as this vector, and let's say we're going from u to v. And if you're going from u to v in that direction, then this must be the vector v minus u. Now, why that's the case, I think, is pretty easy to see visually, because if you were to actually extend the green vector like this, parallel to that green vector previously established, and then this vector u, if we were to kind of duplicate that over here, parallel to that original vector u, then notice that the diagonal of this parallelogram between these green and these red vectors is indeed v. In other words, it's the sum of these two vectors. So u added to this green vector must be v, and notice when you add u to v minus u, the u's cancel and you indeed get v. So this is something we could have spoke about previously in the previous video discussing vectors. It's a visualization of subtraction, in other words, but really what we needed is the visualization for addition, and that kind of comes about actually from that visualization. Anyways, let's see if we can use that to our advantage to try to prove this. If you literally imagine this as a two-dimensional triangle just kind of planted on the board, that's fine. But in reality, it's actually on this plane that kind of extends into 3 dimensions. But anyways, we'll kind of visualize it like that. And what we really need is actually the lengths of these sides of the triangle, and what we're going to use is law of cosines. And that's basically the main tool used in the proof. So once we have that, then we're kind of done, honestly. It was really just this we needed, and then law of cosines. So just to kind of show you, we have this triangle with angle theta. This side length is just the length of the vector u, which is the magnitude of u. And here we have the length of this vector v, which is the magnitude of v. And then we have this guy, which we've already established is the magnitude of that vector, where that vector is v minus u, actually. Perfect. So now what law of cosine says, if you don't remember, is that the square of the side opposite of our angle, so v minus u magnitude squared, is equal to the sum of the squares of the sides that the angle lies between. So that's the magnitude of u squared plus the magnitude of v squared minus 2 times those lengths, u and v, magnitude of u, magnitude of v, times cosine of the angle between them. Perfect. So we can kind of see we have this part, which is indeed the right-hand side of our equation. So somehow we need to make this look like that. Now what I'm going to be using, again, are just the properties that we established previously. Now this is a square. This is a square of what? Of a magnitude. And we saw a property that said that if we have a vector, I guess we called it, was it V or A? I think we used V. I may have used A, but let's say it's A. If we have the magnitude of a vector A squared, then that's the same thing as A dotted with A. So we can say that this magnitude squared is literally just V minus U dotted with itself. Okay. And then we had this property of distribution of a, well, let's see. So here we have a vector and a vector. We can think of this as a sum of two vectors. So the property I'm going to use right now isn't super obvious based on the properties we saw previously, but it's certainly true that you can literally just FOIL this out. So we get V squared, in other words, V dot V, which instead of me writing V dot V, I just know V dot V is the magnitude of V squared. And then if you, so that's V times V dot V, and then V dot U, it's going to be negative, so it's going to be negative. Let's do a U dot V like this. And then here, negative U dotted with V is also another negative UV. Notice they're like terms. So these are the same number because they're dot products, so we can really write this as minus 2 U dot V. So I'm leaving out some details, but it's there. And then negative U dotted with itself, negative U, is positive U dot U, but U dot U is the magnitude squared. Now the reason why this foiling works is because we're basically taking the dot product of a vector and the sum of two other vectors. So you can think of this vector as X dotted with V added to negative U, something like that. And notice we had this distribution of dot products over vector multiplication, and we end up getting this. And then if you replace X with V minus U, then you can distribute U back in, and you basically just get foiling out, which is kind of interesting, but again, just take my word for it that foiling works, and we're okay. And now what? Now I think we're basically done, because if you compare this to this side, we have U squared in magnitude of V squared, minus 2 magnitude of U times magnitude of V times the cosine, I need to erase this image unfortunately, times cosine of the angle between them. Perfect. And now what? Well, now you can literally just subtract magnitude of V squared, magnitude of U squared, and then divide both sides by negative 2. Those cancel out, and you indeed get that U dot V is equal to the magnitude of U times the magnitude of V times cosine of the angle between. So I hope it wasn't too sloppy, but yeah, it's definitely just using law of cosines and then some of the properties we previously established. And one of the big ones was that when you have a magnitude square, it's that vector dotted with itself. Awesome. So we achieved that equation. So I'm going to write a tombstone just to show that we've completed the proof. And now we're going to move on to a corollary, which is just, it's just literally rewriting this a little differently. And then from there, we can discuss a new definition and just keep talking about things that relate to angles between vectors. Okay, so this is the corollary of the previous theorem, which is literally just dividing both sides of the original equation we saw in that theorem by the magnitudes. So we get cosine of theta by itself, essentially. And cosine of theta is just, again, here, the dot product of two vectors, u and v, divided by the magnitudes of those vectors, the product of the magnitudes of those vectors. Where theta, of course, is the angle between those two vectors, u and v. And I think that's all I really want to say here. If you haven't seen the word corollary before, it just means it follows from the previous theorem. It's an application of that theorem, basically. Or a theorem resulting from that theorem, like a specific scenario of that. Anyways, moving on, let's use that in this example to find the angle between these two vectors, u and v. All we need to do is dot these and then take their magnitudes, the product of the magnitudes, and divide. That'll give us cosine of the angle. Then we can take cosine inverse to get the angle by itself. So let's notice that u dot v in this case is going to be 2 times 5 plus 2 times negative 3 minus 1 times 2. So I'm just looking at these guys, 2, 2, negative 1, and multiplying them respectively with those guys, 5, negative 3, and 2. Now if you add these results, the results by the way are 10, negative 6, and negative 2, that's notice 10 minus 8, that's just 2. So the numerator of this is going to be 2, that's fine. Now what about the magnitudes? Well, the magnitude of u is going to be the square root of the sum of the squares of those. So that's 2 squared plus 2 squared plus negative 1 squared. We actually saw this exact one before. Well, not exactly, but it's super similar. And it was just, it's 4 plus 4 plus 1, which is 9. So the square root of 9 is 3. So we know the magnitude of u is 3. Perfect. And the magnitude of v, I think we can squeeze in here. Let's see. So it's going to be the square root of the sum of the squares of those, which is 5 squared plus negative 3 squared plus 2 squared. And let's see. 5 squared is 25. 25 plus 9 plus 4. Let's see. 9 plus 4 is 13. And 13 plus 25 is 38. That's not very good. Square root of 38. I think that's right. Let me just do this real quick here. So that plus 13, yes, is 38. I was just trying to do it in my head real quick. But yeah, it's a square root of 38, which isn't very nice because it doesn't simplify in a nice way. But that's okay. It's still a number. All right, so now what? Well, now we know that cosine from the previous corollary of the angle between these two vectors must be the dot product, which we found to be 2, divided by the product of the magnitudes, which is 3 radical 38. And this implies, then, that the angle itself is cosine inverse of that result, 2 over 3 radical 38. So now I'm going to use my calculator to find out what this is. You can find it in radians or degrees. Degrees is, I think, more intuitive, but I'll show both right now. Okay, so my calculator gave me about 1.46 if you round. That's in radians. But if you want to write this in degrees, it's 83.79 or 83.8. You can round this to 84 degrees if you want. But either of these are okay. I'm just actually going to box this exact one, because I like exactness, even though it doesn't look as nice. But yeah, I don't think that's too bad. So there we go. We actually found the angle between them, which is pretty interesting that we can do that. So that, I think, is a pretty nice achievement in this section. And then the next thing we want to discuss is this word orthogonal. So we say two vectors are orthogonal or perpendicular if the angle between them is pi over 2 or 90 degrees. So we know what that means in a two-dimensional case. In a three-dimensional case, it's kind of the same image you get in 2 dimensions, but just kind of imagine floated around somewhere in 3-dimensional space. All right. So one nice consequence of this definition is that if you actually apply this directly to this corollary, we get something kind of interesting. Because if the angle between them is pi over 2, then we get cosine of pi over 2 is equal to whatever these two vectors are. So let's say they're u and v. We get this, of course. But the really nice thing again is that what's cosine of pi over 2, if you don't remember, cosine of pi over 2 or 90 degrees is 0. And if you multiply both sides by these magnitudes, which are presumably non-zero, then you end up getting that the dot product of these two vectors, u and v, is 0. So that's interesting. That basically says that if the dot product between two vectors is 0, then this implies that the two vectors are orthogonal. In fact, this is an if and only if statement. If two vectors are orthogonal, then their dot product is 0. I kind of hesitate to say it's if and only if, because if they're both the 0 vector, then it's a little funny because the 0 vector has no length, it has no magnitude. So you can't say that really the 0 vector is perpendicular to itself. I guess you kind of could say that, but it gets a little weird. So at least we can say that if two vectors are orthogonal, then indeed their dot product is 0. So that's nice that we can check it to see if two vectors are perpendicular or not by just taking their dot product, and if it's 0, then they must be perpendicular. So that's nice. And we're going to take a look now at something more to do with angles between vectors. It's going to get a little weird, but it's still kind of fun. And well, we'll see that right now. So I won't hype it up. But we'll take a look at that right now, and then we'll move on to something a little different, and that'll be the end for the video finally. Alright, so like I said previously, this is where things get a little weird. These are called the direction angles and direction cosines of a given vector. Now the direction angles will be denoted by the Greek letters alpha, beta, and gamma, and the direction cosines are just cosines of these angles. So I try to draw an image here, and let's see if it comes out okay. So here we have this point in three-dimensional space. Let's say this point is, I guess, v1, v2, v3. We're going to create a vector v going from the origin to this point. So this is the vector v. Now we have these angles. Now, the direction angle alpha is from the positive x-axis. So from the positive x-axis to this vector v, we have this angle alpha, like that, which is pretty hard to visualize, but basically this angle is in the direction of this kind of plane that intersects the vector and the x-axis. Similarly, if you have a plane intersecting the y-axis and the vector v, you get this angle between those, which is beta. And if you do the same thing with the plane intersecting the two lines or the axes, v, the vector v, and the axis z, the z-axis, you get this angle, which we call gamma. Great. So now, what we're going to do basically is we want to find these angles, and what we know is that, well, this distance here actually is going to be v1. It is the x component of v, which we call v1. This distance here would be the distance in the y direction, which is the y component of v, which is v2, and this distance here is its v or z direction, which is v3. Okay, so that part I think makes sense. But now what I want to do is I want to say, well, the angle between them. Notice if we actually consider these unit vectors in those directions, we just get the unit base vectors I, j, and k, if you remember those from the previous section. So I'm going to try to draw hats on them, but the image looks a little cluttered and kind of small. But I hope you can see that I, j, and k. And the angles between those and the vector will be the same between the x-axis, y-axis, and z-axis in the vector itself. So basically what I want to do is I want to say, for example, with cosine alpha, I'm going to say that that is, remember what we previously saw, is the dot product of these two vectors, which is going to be v and I. So it's going to be v and I, like that, and divided by the magnitudes of v and I. And the really nice thing about I, and similarly j and k, their magnitudes are 1 because they're unit vectors, and that part I think makes sense. And v dot I, notice, is just v1. That part I don't think is too hard to verify. In fact, I'll do it over here. V is v1, v2, v3. And if you dot that with I, dotted with I, which is 1, 0, 0, notice what you end up getting is that these two multiplied by 0 just 0 out, and you just end up getting v1 anyways, divided by the magnitude of v. Perfect. And very similarly, you get the same thing for cosine of beta and cosine of gamma. So cosine of beta will then be v2 over the magnitude of v, where cosine of gamma is v3 divided by the magnitude of v. Kind of running the space there. But what's really nice here is that we can actually multiply both sides by the magnitude of v, and then we'll get that, well, v1, v2, and v3, which together combine to just give us v, is equal to this vector whose components now are the magnitude of v1, magnitude of v, I meant to say, there we go, times cosine of alpha. So notice that's just me solving for v1 here, we're multiplying both sides by the magnitude of v, comma, for v2, similarly, that's going to be magnitude of v times cosine of beta, and then finally, very similarly for the third one, we get magnitude of v multiplied by cosine of gamma. And that should be a vector symbol. Perfect. And if we actually scale out that magnitude, we just get the magnitude of v multiplied by cosine alpha, cosine beta, cosine gamma. Perfect. And even further, if we wanted to divide both sides by, because this is v, the vector v, if we wanted to divide both sides by the magnitude of v, we'd end up getting that the unit vector that's in the same direction as the vector v has components that are the direction cosines of that vector, which I think is really nice. In fact, we can use that in this example here to find the direction angles for u. So the first thing we want to do is we want to notice that u we can, well, write kind of like this. So first let's take the magnitude of u, which we know is the square root of the sum of the squares of its components, which is 1 squared plus 2 squared plus 3 squared, which notice is just 1 plus 4, which is 5, plus 9, which is, 1 plus 4, yeah, that's 5, plus 9 is 14. That can't be reduced, unfortunately, but that's okay. And then we can then say that, I guess we can solve for cosine alpha, cosine beta, cosine gamma by just using these results here. But really what I want to say is the following. I want to say that u can be written as the magnitude of u, which is radical 14, there we go, multiplied by cosine alpha, cosine beta, cosine gamma. And again, if we divide both sides by radical 14, we just get 1 over radical 14, 2 over radical 14, and 3 over radical 14. So essentially, cosine alpha is equal to 1 over radical 14. Cosine beta is equal to 2 over radical 14. Cosine gamma is equal to the third component, which is 3, over the square root of 14. And then we can use cosine inverse to find out what alpha, beta, and gamma actually are, which are the direction angles. Now I already did this previously on my calculator, and I got about, I'm going to write these results in degrees though. So I got about 74, 58, and 37 degrees. 74, 58, and 37 degrees. Let me just double check real quick. Yeah, that sounds totally correct. So that's just taking cosine inverse of both sides and rounding to the nearest degree, basically. So it's nice that we can do this, but actually what these angles mean, remember, are these angles that are kind of intersecting the axes, the x, y, and z axis individually with the vector v, and you get this kind of plane. So those angles, those weird direction angles, can actually be found pretty simply, which is kind of nice. So it's a good result here. And then the next and last thing we'll be discussing in this section finally involves projections, where you'll be taking a vector in three-dimensional space and projecting it onto another vector, and you're basically looking at a shadow, basically, and there's a way to find that vector. So let's take a look at that right now, and that'll be the end for the video. Okay, so now the next thing I wanted to discuss again was projections. And we say that the projection of u onto v, or proj sub v of u, is the vector resulting in projecting the vector u onto the vector v. Which I know sounds a little confusing, but with this visualization it should kind of help. Now, these of course are two vectors you can imagine in three-dimensional space, but just for simplicity we'll kind of treat them in two-dimensional space, just so it's a little easier to view things. And what we'll actually kind of need is this pretty simple idea, but before we get to that idea, let's just kind of see the visualization of the projection. So imagine projecting u perpendicularly onto v by this right angle, and this resulting vector you get in the direction of u is the projection of u onto v. Now this is a kind of typical setting, but in a very maybe non-typical setting, you may have something like this, where u and v are not really in the same direction, and its projection will actually be in the opposite direction as v. But it's still a long v, so you can say it's the projection onto the extension of v, maybe something like that. Also notice, depending on the length of u, the projection could actually be larger than v. And in fact, what this really tells us, it's a kind of a good hint, is that really this vector here, which I should have labeled already, is again projection of u onto v. So the subscript's always what you're projected onto. It's a nice way to remember that. Is just a scalar multiple of the vector v because it's in the same direction already. So they just differ by a scalar multiple. So in fact, something we'll be doing that's a kind of clever thing to do, I think, is we'll be taking a look at the unit vector that is in the same direction of v, which notice is v divided by its magnitude, and then we'll multiply it by the length of this projection. So by the way, the length of the projection is sometimes called the scalar projection, where this projection is the vector projection. And the scalar projection is known as the component of u along v. So this is just the magnitude of the projection. That's all that really is. Okay, now what? Well, now that we have that idea, let's just consider the angle between u and v, and then kind of consider some trigonometry, some right triangle trigonometry for a second. So notice that, well, if this is the magnitude of u, then what does this have to be? Well, notice the projection of u onto v, the magnitude of that is this component, what we just defined as the scalar projection, basically. So I'll kind of think about that for a moment. In fact, I guess we can call it something else. It really doesn't matter, but what it ends up being actually is just the magnitude of u times cosine of the angle. And I think that's pretty obvious because if you kind of just take a look at cosine of the angle, it's this side adjacent divided by the hypotenuse side. And if you actually divide them, the magnitudes cancel and you indeed get cosine of the angle. So I wanted to maybe call it something else and go from there so we can see that, but long story short, it's just the magnitude times cosine of the angle. Nice. So now that we have that, that's the component. So really what we have found is that this is really just equal to the magnitude of u times cosine of the angle between. But what do we notice about cosine of the angle between u and v? Well, from what we previously saw from the corollary, this is just, well, the product, or dot product, I guess you can say, of u and v divided by the product of the magnitudes. Which is really nice because notice in this case what happens with the magnitudes of u, they end up canceling out, and we've actually found out that the magnitude of the projection, which is the component or scalar projection, is the dot product of u and v divided by the magnitude of the vector that we're projecting onto. Now that is a very, very important result. And beyond this, what we can say now is, I think, an even more important result, is the projection of u onto v is this length multiplied by the unit vector that's in the same direction as v. Because the unit vector will have a magnitude of 1, and if you multiply that by this magnitude, or by this value, you get that magnitude. So it'll be that same vector, because the direction's already taken care of, basically. So you end up getting this guy, which is its magnitude, multiplied by the vector, unit vector, in the same direction as v, which we know is v divided by the magnitude of v. And in fact, really we can write this as, let's think about this for a moment. Let's be a little careful. It looks kind of funny. And the reason why it looks funny is because it looks like if you just dot the v's together, you get complete cancellations. You have to be a little careful. Because v dot v is just the magnitude of v squared, and then the magnitude of v times the magnitude of v is the magnitude of v squared. They cancel and you just get u. So we don't want to say that this projection is just equal to u itself. And I know it kind of seems a little fishy, but it ends up being the case that they're kind of equivalent. We just have to be kind of careful. And the reason why that isn't actually the case is because dot products don't actually have the associativity law. So taking the dot product of u and v first, and then using that as a scalar multiplied to v is not the same as taking the dot product of u and v first and multiplying that scalar to the vector u. So I know that part's a little subtle, but just believe me that this is not the same as just the vector u. If you're not careful, it may look like it cancels out to just be u, but it's not quite the case. So what we can do though is we can actually bring this denominator in and write this as u dot v, divided by the scalar squared, that multiplied by v. Now let me box this. This is the important result. This result's okay. In fact, we'll need that in this example, but anyways, let's just carry on, not to make the video too long. It's longer than it already is anyways. So I want to find the scalar and vector projections of these vectors, well, of this vector onto this vector. I should say find, I didn't write that. That's okay. So I want to find the scalar and vector projections of B onto A. So first let's find the scalar projection, which is the component of B along A. And notice that's just the dot product of A and B divided by the magnitude of the vector that we're scaling on, that we're projecting onto, which is A. Now the dot product of A and B is, let me just do that off to the side here. So that's negative 2 times 1 plus 3 times 1 plus 1 times 2. So again, just each of these times each of those, added together, that gives us negative 2 plus 3, which is 1, plus 2, which is 3. Perfect. So that's the dot product. The magnitude of A, if you square these, I think we did this earlier, 2 squared is 4, 3 squared is 9, that's 13. 1 squared is 1, so that's radical 14. Perfect. So there we go. This is the scalar projection, which is again just the magnitude of the projection itself, the vector projection. So that's 1. Now the vector projection of B onto A, gotta be careful how we write these things, is exactly the, let's see if we can see this, yeah. So it's exactly the scalar projection we just got, 3 radical 14, multiplied by what? Multiplied by the unit vector in the direction of A. That's exactly this, because notice that this guy here is the same as the component vector, and this guy is the unit vector alongside A, or alongside V in this case. So it's a unit vector along V, you can say. So in this case for A, it's going to be this vector divided by its magnitude. And that's interesting because we already know that its magnitude is, well, 1 over radical 14, and then multiplying by the vector itself, we end up getting that. And in fact, notice this calculation is exactly this calculation here. The dot product of the two vectors is 3. The magnitude squared is just going to be 14, because radical 14 times radical 14 is just 14. And then scaling that guy into this vector will result in this result here. 3 over 14 scaled to negative 2, 3, 1. And if we actually scale it in, let me write the result above, we end up getting negative 6 over 14, which actually reduces to negative 3 over 7, comma 9 over 14, comma 3 over 14. Not bad. So we've only basically done one example of each topic we've discussed in this video. They were kind of complicated topics, but that's really it. So that's basically all I wanted to say for dot products. I really hope you enjoyed this and found the video insightful. In the next video, we'll be taking a look at the cross product, which is, in my opinion, it's actually a little bit more than dot product as far as complexity goes. So make sure you're strapped in for that one. But anyways, I'll see you in that video. Hope you enjoyed this. Thanks for watching, and I'll see you then.